conference is now starting. All attendees can now hear you.
Good morning and good afternoon to all. My name is Suha Asoilu, and I'm the Director of Operations at Hosokawa Micron Powder Systems. I would like to welcome all of you to our webinar titled Wet and Dry Milling. Before we get started with our presentation, I'd like to give you a brief introduction to who we are. Hosokawa is one of the largest powder processing companies with over $500 million in revenue and 1,500 employees throughout the world. We have a presence in all 5 continents and 12 centers spread across the globe. Our primary objective is to provide solutions in the areas of size reduction, classification, mixing, drying, and containment. Hosokawa Micron Powder Systems, located in Summit, New Jersey, is the unit responsible for the North American market. With a complete engineering staff, test center, and service group, our aim is to provide a one-stop solution to our customers. I would like to remind everybody that, if you have questions, please type them in the question and answer section of it. And what we will try to do is at the end of the presentation, we will try to answer as much as we can. With that, I would like to turn it over to my colleague, Dr. Stein, from our sister company in Germany, Alpine, to start the presentation. Dr. Stein?
Yes, ladies and gentlemen, good morning from Germany. My name is Juergen Stein, and I'm the R&D manager for powder and particle processing at Hosokawa Alpine in Germany. We are located in the south of the country, and with our 10 years old tradition, we are one of the eldest. We are the eldest unit in the Hosokawa group. There are 560 employees working in the 2 divisions, powder and particle processing, and in the blown film division. Let's now start with today's topic, which is wet and dry media milling. And first of all, I will give you a survey over the topics of my talk. I will try to get the next slide here. I think it will take a second from the US to Germany and back. Sorry for this delay. Okay, we have it. So during my talk, I will speak about, first of all, the fundamentals of media milling to give you some theoretical background. I will also talk about the basic types of the mills, of the media mills. Then I go into the technology of dry and wet media mills. We give you some information about possible applications and the plant technology. And finally, some information about an interesting field, which is submicron grinding with wet and dry media mills. Before I enter into the technology of the mills, I have a survey on all the main established types of mills. On the top of this graph, you can see in green color the dry mills, and on the bottom in orange color the wet mills. What you also can see is that all these mill types are covering a range of about 9 decades of particle size, reaching down from 1 meter rocks to about 10 nanometers particles, which can be ground nowadays. The fundamentals of wet milling. This is easy to explain, and on the next slide you can see a very simple mill. It's a very early model, about 20,000 years old, but it's a very, very suitable machine to explain the mechanism of media grinding. You can see here the basic parts of a media mill, which is the grinding medium. It is one only in this mill, and we have a part of the mill, a kind of a support, and in between there is the powder which we want to grind. And with this mill, it is very easy to explain the basic grinding mechanisms which can occur in a media mill. If you take the stone in your hand and you knock on the support, you create a kind of impact on the particles. You can also take the stone and roll it with pressure, and you have a pressure stress on the particles, or you rub the stone on the support, and then you get a shear stressing of the particles. These are the basic types of grinding mechanisms which grinding media can bring over to particles. And this is the same in modern mills. I think the next slide will show what the difference is and what the similarities are. This is a modern grinding mill. We have not only one grinding stone, we have lots of grinding beads inside, but the same things will happen. We have ball-to-ball contacts which create an impact on the particles. We can roll the balls and create pressure, or we can shear the particles between two passing grinding beads. So this is so far the same as in the old mill. However, in the old mill you can take the stone and decide by yourself which grinding mechanism you want to have. This is actually not possible in a modern grinding mill because you have thousands or millions of grinding beads inside. So there will always be a mixture of all these grinding mechanisms in the mill. There is a certain chance to influence that by setting the parameters of the mill, like the rotor speed or the filling ratio of grinding beads or the material or the size of the grinding beads. But you can only create a tendency to get more impact or to more shear on the particles, but you cannot decide to make a single shear stressing in a mill with such a high number of grinding beads. Let's now come to the mills themselves. This slide is showing you a survey on the different types of media mills which actually are existing. First of all, we have a tumbling ball mill, which is a rotating drum in horizontal axis, and the grinding beads are accelerated by the rotation of the drum and falling back, and the grinding energy input is done by the gravity, which is affecting on the grinding beads. If you need more energy input into the mill, you cannot count on the gravity. You have to look for external forces which you can bring into the grinding media, and this can be done in different ways. One is the agitated media mill with a rotor inside, which is rotating and bringing the motion into the grinding media filling. You can also do this by a planetary mill, which has a certain double rotation of the mill and the grinding chambers themselves, and you can simulate a tumbling ball mill grinding under centrifugal forces. Other types of mills are vibration mills, where the grinding body is moving with a high frequency to transfer the energy into the grinding beads, or centrifugal mills, which are doing basically the same but with a lower frequency to create a kind of a rolling grinding media filling inside. For my presentation, I pick out two types of the mills, which is the tumbling ball mill, running with the gravity forces, and the agitated ball mills, which we can apply for dry and wet media milling. I start the technology first with dry media mills. This photo is showing a tumbling ball mill, a very classic type, operated in a continuous way. So we have here a machine with a drum diameter of about 2.5 meters and a length of 6 meters, which is a normal production scale machine for ultrafine minerals grinding. You can see the rotating drum here, the drive unit and the bearings on both sides. The material is fed into the mill from this side here and leaving the machine, in this case, on the bottom on this side of the mill. These mills are usually operated continuously, but not as a single mill with one pass through the mill, which is definitely not sufficient for a very fine grinding. We always have a system with a grinding circuit comprising the mill and the classifiers. I can show you on this flow sheet how this can work. This is a typical ball mill classifier plant, which we always are applying in the minerals industry. The feed material comes from a silo here and is charged into the mill by a dosing unit and is passing the mill in this direction here. The mill is containing grinding beads made of steel or ceramic, and the typical size range of the beads is 10 to 60 millimeters. After passing the mill, the material is being discharged and conveyed to the classifier. In this case, we have a typical arrangement with two classifiers, so we can split the material to a coarser classifier, which making one end product, or to a very fine classifier to make a second product, which is collected in the filter. And so this is a plant that can produce in parallel two different products. The coarse fractions from the classifiers are being recycled to the mill and going back into the circuit again. Alternatively to the tumbling ball mill, we can also choose agitated media mills to have the chance to bring a higher energy into the grinding chamber. And this is a type of mill which we are supplying. It is called ATR. It's a vertical cylindrical grinding body and has a vertical shaft with rotating elements. And this mill is filled with the grinding beads up to the top. And the rotor is in slow motion of about 2 to 3 meters per second. Typical mill volumes are in the range of 1,000 or 2,000 liters, with power installed reaching up to 315 kilowatt. So the power input which we can create with such a mill of 180 kilowatt per cubic meter mill volume is significantly higher than a tumbling ball mill has. These mills also are operated in a closed circuit system with classifiers. I can show you this on the flow sheet. In the center you can see the media mill. The grinding beads and the product is fed from the top into the mill, and both beads and product is passing through the mill, being ground and then discharged by a conveyor screw out from the mill. Beads and product are separated on a vibrating screen. The beads will be collected in a special hopper and being recircled into the mill by a bucket elevator. The product passing the screen is going on into a classifier, and the fine product collected in a filter is the end product of the plant, and the coarse fraction is being recycled via the bucket elevator into the mill again. So this is also a closed grinding circuit with mill and classifier. To create such a ultrafine grinding system, it is important to have a mill which has a high energy input and can be operated with small grinding media. However, it is very important also to have an appropriate classifier for the typical end products you want to obtain with this plant. And this slide is showing you a selection of classifiers which we can offer together with such plants for the grinding circuit. On the left side you see a circuit air classifier. We call it a Ventoplex, which is dedicated to make classifications in the range of 30 to 300 microns, so it is more on the coarse range of the products. We have a spiral flow classifier, ASP Stratoplex, which can do a little finer. It is designed for high capacities and low pressure loss, so very economic classification. And we have very fine classifiers, which is the ATP Turboplex classifier or the TTC Turbo Twin with a special wheel geometry, which can go down to 5 or even 2 micron separation cut. Some details of these classifiers can be seen in the next slide. On the left side you see the Turboplex classifier in a special arrangement with multiple wheels. So in this case it is 6 classifier wheels in one classifier housing. And with this classifier it is possible to make very fine separations with high capacities. This can even be improved with a new type of wheel, which we call the NG new generation wheel. It has a special blade geometry. It is creating a forced vortex separation inside, and this classifier wheel is able to go down with cut sizes to about 3 micron, or in the TTC wheel, which you see below, down to about 2 micron separation. And the result of such a plant can be seen in the following graph. Green is the feed material, orange is a result of a ball mill classifier system, and the yellow curve is showing a product which is coming from the vertical media mill ATR. What you can see obviously is that we reach the expected, I call it grinding limit of about 1 micron, D50, and even with a high intensity mill, the vertical media mill, we cannot go significantly finer than the bore mill. So it seems there is a limit of grinding, and I will come back to this problem later again when I speak about stabilization of the particles. But first, let's go to the wet grinding. On the top of this slide, you can see 5 different models of wet agitated media mills. This is the basic types which are existing on the market. We have vertical mills with a vertical axis in open and closed design. We have horizontal mills with disc agitators, with pin agitators, and we have also annular gap mills which do not have grinding tools. They just have a small gap to accelerate the grinding beams. We're talking about 2 mills which Alpine is offering in its product line, which is the universal mill horizontal type Alpine AHM, and we have the vertical mill A&R, which is an open type with vertical shaft. The A&R, on the next slide, the machine can be seen, is a machine which we especially apply for calcium carbonate grinding for the paper industry. The paper industry is consuming lots of calcium carbonate slurries in high concentration and high fineness to fill and to coat the paper. And so these mills are designed in big scales only. We have mills up to 9,000 liters volume with 1 megawatt drive, and these are typical sizes for the paper industry, which is consuming these big amounts of slurry. The mill itself has a cylindrical grinding chamber here with a vertical shaft inside. The shaft has agitating elements with wear protection, and the mill is completely filled with grinding media about 1 millimeter size. On the next slide, you can see an example for a plant and the results of products which we can produce with this plant. You can see on the photograph that this is a plant with 6 mills. Each has 450 kilowatt drive and 5,000 liters of volume. You see three mills in a line and 2 lines in parallel, but this plant can be flexibly connected to make a single, a double, or a triple pass grinding, depending on the fineness you want to obtain. And the products can be seen on the graph on the left side. We have ground calcium carbonate slurries with a solid concentration between 75 and 78%. The feed particle size is 325 mesh coming from a table roller mill, and is pre-mixed in a slurry, then fine ground to the required fineness or quality, and finally maybe classified if necessary with screens or centrifuges, and finally stored into big tanks to be supplied directly into the paper factory. You see the typical finenesses required. This was a little bit too fast for this slide. You see the typical fineness for the paper industry. It is reaching from 60 to 80% below 2 micron in the particle size distribution for typical filler materials, and from 90 to 99% below 2 micron for top coating pigments for the paper. The second mill I want to talk about is a very, very universal mill, which you can nearly apply for any product which you want to grind in a slurry. It is the horizontal media mill AHM, and this mill is very flexible in the size. We have a product line reaching from a very small machine called Picoleak with 7 milliliter smallest grinding volume for research applications. You can use it for about half a gram or 1 gram of material to grind, particularly for the pharmaceutical industry. Then the line is reaching up, passing a lab mill, some pilot scales, going up to production machines which can have 1,000 liters volume and 350 kilowatts. You can see the smallest and the biggest machine here on these photos. The matchbox will give an imagination of the size we talk about. On the next slide you can see some technical features of this mill. And first of all, you can see a dynamic bead separator on the rotor and a very fine screen which is separating the grinding beads from the slurry when leaving the machine. So this has a direct dynamical relief, so that means the machine is suitable to run grinding beads down to a very small size which are necessary if you want to make nano grinding. The screen can be exchanged and serviced very easily. The mill can be opened without emptying the grinding beads, so this is a thing of a few minutes only to make a service on the screen. Another feature is the flexible wear protection system. You can see here some examples. This is a mill which is completely lined with zirconium dioxide ceramics and some wear parts made of polyurethane, of steel and of another type of ceramic. So the machine is a kit system, and you can change the rotor and the starter parts made from these materials, polyurethane for water-based slurries, some metal materials, different ceramic materials, and even plastic materials are applicable to this machine. In the following slides I show you some applications of the horizontal media mill. This is an example of a small plant which can grind high quality zirconium dioxide for electronic applications. You see that we are making a product with a D50 around 500 nanometers, which is a very typical size for standard media grinding. The plant itself is comprising two mills. You can operate them in parallel for high capacities or in a serial connection. And for high fineness, it's even possible to put different grinding media size into the machine to optimize the grinding for very fine particle sizes. The next slide is showing a small plant for titanium dioxide processing. And you also can see that we're reaching down to about 300 nanometers particle size. But actually this is not a real grinding, this is a dispersion of agglomerates. Titanium dioxide is in this particle size distribution are only agglomerated primary particles, and by circuit grinding we can obtain the primary particle size of this product. A special application is shown in the next slide, which is the photo is showing a 200 AHM model, which is a production machine in GMP design, which is applied for the wet grinding of active pharmaceutical ingredients. You see all the machine is made in stainless steel with cleaning systems and monoblock design. So it is applied for the special requirements of cleaning and handling of the pharmaceutical industry. And on the graph here you can see an example for a grinding of an active ingredient, which is starting on a maybe 10 micron size and reaching up finally to a nano size of about 150 nanometers. And these particle sizes are very important for insoluble active ingredients which are dispersed in a liquid to increase the bioavailability of these ingredients. Finally, on the next slide, we have an application for real nano grinding. This is an example to grind aluminium oxide in water. And we have used a 90 AHM plant, which is a complete, we call it a plug-and-play system. Everything which is needed is integrated in this rolling box here. We have a pump, an agitator with a cooling tank, pressure liquid system for the shaft seal, and the mill itself, which is a 1 liter mill for lab applications. And what you can see here is that we have made a real grinding of aluminium oxide particles, reaching up to a particle size of finally 50 nanometers D50. But to be honest, this is not just grinding, it is a special recipe of the slurry, which is containing stabilizers, surfactants, to make this agglomeration and stabilization of the fine particles. I also come back to this topic a few slides later. But before I speak about stabilizers, I want to give some information about the grinding media, because it is not the mill, not the media mill who is making the grinding. It is actually the grinding beads who have the contact to the particles, and the grinding media are the tool to grind. So it is extremely important to choose the grinding media in the right manner. And I have listed here some properties, some criteria for the grinding media. First of all, we have to select the right size. Grinding media for agitated media mills are available from 50 micron to 3 millimeter size, approximately, maybe 10 for special mills. And we have to look first at the feed particle size to be sure that the grinding media are not too small to obtain a grinding effect on the big feed material. And we also have to look on the required end fineness. And for very fine materials, we need a high number of very small grinding media. And so it's important to find the right grinding media size in respect to these both particle sizes here. We also have properties like hardness, strengthness, and so on, which have influence on the selection of the beads. And finally, we have to look on the contamination, because media milling always creates abrasion, which is going from the mill into the product. This contaminates the product and is reducing the lifetime of the mill and the grinding media. And so it's also very important to choose the right material of the beads, which can be metal material, glass, different ceramic materials, or plastic materials. To optimize the performance of our mill, you can purchase also very specified grinding media, which are called power beads, and we supply them together with our mills. Just to imagine the importance of the media size, I've prepared this slide here. It's showing two grinding beads with a diameter of 1 millimeter, which is this blue curve here. It's reaching up to the top of your room. And in between, you can see in red color here a 2 micron particle. And you can imagine that it's not too difficult to hit this particle to crush it down with these two beads. But if you decrease the particle size to maybe a few hundred nanometers, you see these small black dots here, and you can imagine how difficult it comes up to hit these particles to make a crushing of the particles. So this slide can show impressingly how important it is to choose the right size of grinding beads. And in this case, for such small particles, it's important to decrease the size of the grinding beads and increase the number of the beads to be sure that all these small particles can be crushed during the grinding. And the two figures here, the stress intensity and the stress number, could you please switch back one second? Are determining the grinding effect. The stress intensity is more or less the kinetic energy of the grinding beads, and has just to be sufficient to crush the particle, not too much and not too less. And the stress number is indicating the number of stress events during a grinding which is being effected on a particle. And for very small nanoparticles or submicron particles, very important to have a high stress number. And finally, the grinding energy is being calculated from the product of stress number and stress intensity. This is a means to calculate and optimize a grinding media mill. Yeah, and on the next slide I show you another, let's call it a problem of grinding of media mills, which is the residence time distribution. A continuously operated mill where the product is coming in on one side, passing through here and leaving by the screen on the other side, has not a motion like it's characterized by the red arrow here. It is not a straight flow through the mill. There is a heavy turbulence like the yellow arrows show here. So some of the particles are staying a very long time in the mill, others are passing through very quickly, which is resulting in a wide residence time distribution and accordingly also a wide particle size distribution. And it does not help a lot to change the geometry of the mill. It can have a little effect, but not significantly. But another means to influence the particle size distribution is the mode of operation of the mills, which is shown on the next slide. You see here with the yellow mill, this is the single pass operation which I have shown in the slide before, resulting in a very wide particle size distribution. If we increase the slurry flow through the mill, the influence of the turbulence is decreasing, and we get a smaller steeper particle size distribution, as you can see for this blue arrangement, where we put 3 mills in a serial connection. This is extremely interesting for us because we are selling mills, and if you want to make 20 passes, we can sell 20 mills for that. This becomes very complicated, so there are 2 other modi to operate the mills which are easier to handle and cheaper in investment. The red mill is characterizing one big mill again, and we put 2 tanks around the mill and running the material from one tank through the mill and then going back through the mill again back to the first tank. So this is a kind of JoJo grinding, and we repeat this as often as we want, 3 times, 10 times, 20 times if needed. And the result is characterized by the red curve here, a very steep particle size distribution. However, this operation is a little bit difficult to control with valves and liquid level sensors and so on. And some people make life easier and make a simple circuit grinding. They take the same mill size and run the material just in a circuit with 1 tank and 1 agitator. The resulting curve is the green one, which is still a steep particle size distribution, not that good as the red one is, but sufficiently. The effect comes from the mixing statistics of the tank, which has an influence on the residence time in the mill too. But this is a very easy process which can be applied for many production plants. Yeah, so far the milling technology. I would like now to talk about this supposed grinding limit, which I have minded some slides before. There was dry milling, and a dry milling example which ended up around 1 micron. And the reasons for that is that the particles, the finer they come, the bigger are the forces which try to attract the particles to each other and to form agglomerates of the particles. You can see this here. The particles are stressed by the grinding boards, reaching a certain fineness and immediately agglomerating. So the grinding beads have to destroy the agglomerates again against the attracting forces, and then a reseparation occurs, and then again agglomeration. So there is no grinding progress anymore because there is no crushing of the particles. It is always a re-agglomeration by the attracting forces. The other thing that can happen, this is valid for dry and wet grinding. For dry grinding, an additional effect occurs that the grinding media are coated with sticking particles and forming a big layer around the grinding meats, and so the grinding forces between the particles are blocked, and not a real efficient grinding can occur anymore. But there are means to do something against it. So we have to try to influence the particle interactions. We try to influence the surface properties of the particles, which is shown in the next slide. And if we put some additives, some grinding aid into the powder, which influences the charges on the surface, or other things, I show this on the next slide, then it is possible to shift the particle size distribution away from the 1 micron grinding limit into the submicron range. You can see some examples here of different additives and also additive mixtures, which we have done in a lab machine and a small planetary mill. And you see that nearly all of the particles are now in the submicron range, with a T50 average particle size reaching down to about 300 nanometers. So this is still R&D work which we are doing. It is not state-of-the-art. There are some industrial processes of, for example, calcium carbonate grinding, where we already use some grinding aids to influence the agglomeration behavior of the powder. but we cannot obtain yet such fine particle size distributions in an industrial dry milling process. This is different to wet milling. We are many steps further in wet milling, and on the next slide I can show you the mechanisms of stabilization which we can use in wet milling. There are three different mechanisms which we find. One is the electrostatic stabilization. This is creating a charged layer around the particles, and if two particles have the same charge here, the attracting forces are blocked and the particles cannot agglomerate anymore. We can alternatively do a steric stabilization where we put some long chain molecules on the surface of the particles, and the long chains keep just, maybe we call it mechanically, the particles apart from each other, so they can also not approach each other because they are blocked by the long chains of the additive molecules. It's also possible to combine electrostatic and steric stabilization and get electrospherical stabilization, where we have some molecules with charged groups at the end, which and the charges additionally support to keep the distance between these particles. And in liquid slurries, it is very easy to bring in such additives. For example, if you have a polar liquid, you can do the stabilization electrostatically, just as it is shown here in this graph. This is our curves for three different materials as examples, and showing the value of theta potential, which describes the charged layer around the particles, and the pH value of the slurry. You can see different materials have different behavior. If you look at this green curve, it is obvious that we can stabilize the particles in the acidic range of the slurry. In pH values from 0 to 6 or 5, we have significant theta potential, which affects like this here and keeps the particles stable in the slurry. If we go down here to the zero charge point, we come into the field where we have agglomeration. The charges disappear and the particles will stick together. The red curve shows a different behavior. In this case, we would put some base into the slurry to make a caustic pH value, where we have a good theta potential to keep it stable. If we have products which do not react on the pH value like the yellow curve shows, then we cannot make an electrostatic stabilization. We have to choose one of the other methods here. Yeah, and this is the trick to come to nanoparticles, and with this example I can show how successful and how easy this can be. This is a standard grinding system with a horizontal AHM mill, just a circuit grinding with pump, tank and the mill, and we have ground an inorganic pigment which finally reached down to an average particle size of 19 nanometers, just by electrostatical stabilization, by shifting the pH value to the appropriate theta potential. Yeah, and this brings me to a certain conclusion. We can identify three important tools to obtain ultrafine milling. That means bringing a media milling into the submicron range, or even into the nano range. So this is valid for dry and wet grinding. We find out that media mills, dry or wet, are the suitable machines to bring in the necessary energy and impact events to get a very fine or ultrafine milling. We have to choose the right media. Especially the media size is very important, and for nano grinding we go down to 50 micron or 100 micron beads to make this economical in a short time. We also need high performance material for the grinding media to avoid contamination of the product. And finally, the most important, we have to choose the right additives to influence the surface activity, surface interactions of the particles, to avoid the agglomeration and to stabilize the fine ground particles. Yeah, in the next slide I can show you some field of application. It just gives you a survey of the versatile applications for media mills for ultrafine grinding, and you can see nearly any industry can have a benefit in this. Yeah, and this is the end of my presentation. I just feel free to show you some exhibitions which come up in the next month, and where Hosokawa is participating. We have two exhibitions in Germany. One is the Powtech, which is one of the most important European exhibitions about powder processing in September or October in Nuremberg, Germany. We have next year in May the AHM in Frankfurt, and there are some other exhibitions and events in the United States which are coming up soon in September up to November, and an exhibition in March. You can see this finally on the slide. Yeah.
Well, thank you very much, Dr. Stein. This basically concludes our presentation, and now we're at the question and answer session. And as I mentioned earlier on, if you can submit your questions via writing into the question and answer section, submitting to us, in the next 5 to 10 minutes, we'll try to answer as much as we can. And the ones that we do not cover here, we will take care of it privately in terms of providing you an answer after this webinar is concluded, calling you or sending you an answer to your question. So, you know, one of the things, I guess, one of the questions that showed up, Dr. Stein, is basically what's the energy consumption for the different wet ground GCC qualities?
Yeah, that depends on the fineness we want to have, and this is starting on the low end for a coarse filler material with 60% below 2 micron. The energy consumption is around 35 kilowatt hours per ton related to dry solids, and it is reaching up for the D99 for the 99% below 2 micron material, which is around 200 kilowatt hours per ton.
And you know what? I guess I'm at the same time transferring some of the questions to Dr. Stein for him to kind of pick through the ones that you know, would, I guess, have the most generic appeal to. So, you know, one question I have here, Dr. Stein, as you look through the rest of them, is a continuous dosing of additives needed during the wet nano milling process?
Sorry, I didn't get that. Could you repeat?
Sure. Is a continuous dosing of additives needed during a wet nano milling process?
It is, yes. We have always to control a constant pH value or a constant conductivity in the material, and we always have to keep the optimum conditions for the stabilization. So it is needed to dose the additives constantly, and it's needed to control some properties of the slurry to have an image what we have to do. And this can be done by measuring viscosity, by measuring conductivity or pH value, or even measuring the particle size directly in line.
Next question I have is, can any of your equipment be used to make below 100 nanometer API? It's a very generic question, I guess. So, you know, as far as, you know, you have shown that you have done a D50 down to 19 nanometers, maybe this question might need to be a little bit more specific in terms of us being able to answer it.
Yeah, basically we can say that it's possible to reach this particle size, but we have carefully to look on the suitable additives here. And this needs some basic considerations about the chemical activity of additives and the grinding material. And usually it needs some testing to find the optimum conditions for this grinding.
Okay. sorry?
We can intensify this answer by email conversation later if needed, yes.
Yes. And another question here is, does the steric stabilization also play a role in dry milling process?
Yes, it does. The examples I have shown with some mixtures of additives, this is containing materials, molecules for steric stabilization or electrosteric stabilization. In dry powders, it is usually not possible just to put a charged layer around the particles because the polar medium around the polar liquid is missing. So in dry milling, it is usually a sterical stabilization.
Okay. Here's again somewhat specific question. Have you had any success grinding tough polymers such as nylon 6 to less than 50 micron size?
50 nanometers.
I'm guessing it's the attendee was probably trying to say 50 nanometers.
I have to look in our test files. I cannot answer this question at the moment, but I can do this later when I have checked the test files and give some detailed information on this product.
Okay, maybe just keeping it out of generically, in terms of polymers, have we done any testing on polymers basically in the, let's say submicron range?
I'm not sure whether we were successful with polymers yet.
Okay.
There are some sorts of polymers which can be ground under certain conditions, but it's very difficult to do that.
Okay. I have one other question here, and that's more on the tail end of, I guess, a wet milling system. How would you dry the wet milled material to maintain particle size for the dry products?
This is usually not possible to maintain the particle size for the dry products, particularly if you go into the submicron or even nano range. During drying, the particles will definitely agglomerate again. But depending on the final application, this may not have an influence because if we once have created the primary particles in the required fineness, they may be dispersed in the following process. I give an example which is a polymer compounding. We can grind the particles down, dry them, and if we dose them into the extruder for the polymaze, by the shear stress, they can be deagglomerated again to a certain particle size.
Okay.
But drying is very difficult.
And one more question here in terms of bead sizing with respect to the end fineness. One of the attendees is asking, if they're trying to make 100 nanometer particle size, what size media should be used? I guess again, there might be some generic approach to this, not knowing exactly the material.
Yeah, but the particle size gives an indication, and for a 100 nanometer product, I would choose grinding media around 200 or 300 micron. Maybe a little bigger if we have a coarse feed material, and maybe it's necessary to switch in 2 steps from coarser grinding media to fine grinding media. But for a 100 nanometer product, we usually do not need the very fine grinding media of 50 microns, which cause finally big problems in the production process. In the lab it's okay, but for production, for availability in the production and liability of the and availability of the process, it's difficult to operate big mills with 50 micron beads. I would recommend 200 or 300 micron.
Okay, so basically what you're saying is, besides from the end product fineness, also the feed particle size also plays an important role in the sizing of these beads, basically.
Yeah, you can imagine if you have a 100 micron feed particle and you have 100 micron beads, it is not possible to crush the big particles with the small beads.
You know what? Again, coming back to the drying, Dr. Stein, one of the questions is if you want nanoparticles, can you wet mill then spray dry the slurry?
Yes, this is one of the common methods to spray dry, and you create agglomerates of 100 or 200 micron. which have agglomeration forces which can be destroyed later on. So it is a very soft agglomerate, and if you put it, for example, into a ceramic casting, then the primary particles will occur again, and the spray-dried agglomerates can be destroyed in the downstream process.
I'm going to take one last question here, just to keep things in time frame that we've allowed. The last question I have is alumina of 4 to 5 millimeter size suitable for both dry and wet grinding?
You speak about aluminum material to be ground?
Yes.
No, 45 millimeters. No, 4.5 millimeters is too big for wet grinding. We use the 4 or 5 millimeters beads just for the dry vertical media mill. For the wet media mills, we are going down to 2 millimeters maximum, preferably 1 millimeter or smaller.
Feet size, basically.
Feet size, yes.
Okay. I think this is where we're going to stop with the live question and answer session. And what we will do, as I mentioned, is we have all the additional questions that have come in. And you have seen our contact names up on your screen as well. In the U.S., it's me, Suha Soilo, and outside of North America, Dr. Stein. And what we will do is we will contact you individually to provide you with the answers that you need. Thank you very much for joining us today, and I want to thank Dr. Stein again for his support. And again, hope to have you guys with us on the next webinar that we'll be having. So thanks again.